these sampling distributions.
The Seattle Epidemiology Research and Information Center, in collaboration with the Department of Veterans Affairs, the VA Employee Education System, and the University of Washington Department of Epidemiology, present the 2002 VA Epidemiology Summer Session.
Good day. My name's Gail Reiber. I'm the director of the Summer Epidemiology Program, and I'm happy to welcome you all to General Biostatistics. The professor that's going to be instructing you over the next several sessions is Dr. Marie Diener West. She's a professor of biostatistics at the Bloomberg School of Public Health at Johns Hopkins University. Dr. Diener West has been very involved in clinical research, clinical trials, and even serves on VA research review committees. There's a very coveted award at Johns Hopkins University for outstanding teaching that's known as the Golden Apple Award. Dr. Diener West has received this award 4 times for her teaching of biostatistics. So it's with great pleasure that we welcome Dr. Diener West to instruct us with general biostatistics.
Well, thank you very much, Gail. I'm delighted to be here. But first, let me find out a little bit about you. You know, as a biostatistician, often in a social setting, I'm met with a glazed look when they find out I'm a biostatistician. And usually I'm met with these cries of, oh, statistics was my worst subject, or, you know, how to lie with statistics, all of these wonderful things. How many of you have had an Intro to Biostatistics course before? Okay. How many of you have not? How many of you have but aren't willing to admit it? Okay, a few. Okay, but it sounds like it may have been a while for those of you who have had that. So today it will be a little bit of a review for those of you who have had some before. What I have done is I've structured this course into 10 lectures. And so they're really 10 50-minute or so lectures. We'll have 10-minute breaks in between. And although most of this is lecture-based, I will be using Stata as a statistical analysis package to show some examples occasionally, and also some internet-based applets or applications. And of course, I'll welcome any questions as we go along. So over this week, this is our course schedule. What we'll be doing is really looking at an overview of biostatistics today, what some key factors in statistical reasoning are, how we can use descriptive statistics, and we'll start to look at some of the tools of probability and probability distributions to lay the way for making statistical inferences. So today we won't be talking about p-values or statistical significance at all. We'll be laying some of the foundation. We'll move on then to look at methods for statistical inference, namely those of estimation and hypothesis testing. And then we'll move into looking at the use of common statistical tests for one group, for comparing 2 groups, first by looking at means between 2 groups and comparing proportions between 2 groups. And as time progresses, then we'll look at comparing more than 2 groups using analysis of variance, and spend some discussion on sample size and the power of statistical tests and common errors that can take place. And then lastly, we'll look at simple linear regression as a method for looking at association between 2 variables, and we'll end with a summary. So today we'll look at key ideas in statistical reasoning. We'll look at exploratory data analysis methods over this next hour. So over this next hour, I'd really like to place this course in the context of the scientific method of scientific investigation. I'd like us to see what critical role biostatistics and the paradigm of biostatistics plays in the area of scientific investigation and in decision making. We'll look at the fact that not all data are created alike, that there are different types of variables and different types of measurement scales that influence the types of methods that are used. And I'll try to give you a motivating example of scientific evidence from scientific studies, and we'll see first how we can look at data using exploratory data analysis methods. So what is the scientific method? I think that one way of thinking about this is that there are really competing hypotheses about nature. And so the symbols I'm using here are just H0 for a null hypothesis, H1, H2, up through Hn, which are competing hypotheses. So how can we think about this? We can think of a null hypothesis, and for a simple example of looking at treatment A and treatment B. A null hypothesis is that there's no difference between treatment A and treatment B with respect to outcome. Another hypothesis is that treatment A is better than treatment B, or another hypothesis is that treatment B is better than treatment A, or maybe it's 2 times better or 3 times better. So we have competing hypotheses, and typically what one does is design a study and collect data or observations to try to answer a question of interest and address a hypothesis. So we can think of data as providing us then with evidence in support of one hypothesis, or maybe several hypotheses, in evidence of one rather than another. So with the scientific method, what we aim to do is rule out certain hypotheses and find support for others. So in collecting data, we collect observations which provide us with scientific evidence then in the form of those observations to either support or refute certain hypotheses. Now, biostatistics really forms the framework for the scientific method. So first, let's define what biostatistics is. And depending on where we put the emphasis on the syllable, we can look at emphasizing the prefix of biostatistics, that biostatistics is applying statistical reasoning and methods to problems in biology, medicine, and health. Or we can emphasize the second, the suffix, and look at biostatistics as a way of using scientific information, namely data, to describe or draw inference about phenomena in health and medicine. So these are our definitions of biostatistics, but how do we really use biostatistics then in the scientific method? It really consists of these 4 steps. So what's the first step? We said the first step is to really have some underlying question of interest in which we can articulate a hypothesis or a number of hypotheses. So the first step is to generate the hypothesis. The second step is to design a study to collect information to try to adequately answer the question. All of the questions in health and medicine are really questions that we can answer by collecting data, by setting up a study. There are other courses that you can take that focus on how to appropriately design a study and how to appropriately collect data to answer a question of interest. We'll be really looking today at these second 2 steps, the third and fourth step, in which once data have been collected from a study that's been appropriately designed and carried out, that we can look at biostatistics in 2 areas. One is descriptive statistics, where before we look at statistical significance or p-values, where we really just describe the observations and look at the data. The data themselves are meaningful before applying statistical tests to them. So the first area we'll focus on are descriptive statistics, and then the second area is the area of statistical inference, where we aim to use the evidence that we have in the data, in the observations that we've collected, to provide some support either for or against a hypothesis. So it's these 2 areas of descriptive and statistical inference that we'll be focusing on over the days of this course. So what's this first area of descriptive statistics? There are books that are written just on this area of exploratory data analysis. And there was a very prominent, somewhat eccentric statistician named John Tukey, who was affiliated with Princeton University and the Bell Laboratories, who established many of the exploratory data analysis techniques that we'll be talking about today. But exploratory data analysis means really just look at your data. What can you see by looking at your data? How can you appropriately summarize it and organize it? How might one provide descriptive information in tables and graphs that accompany a journal article? And by looking at the data, you can sometimes see important patterns that stand out. There may be anomalies or outliers. There may be forms of the distribution that influence the type of method that can be used. So we'll be looking at techniques for helping us gather some visual impression of the data. So it's this area of statistics, descriptive statistics, that is really hypothesis generating. We look at the data and try to then establish the appropriate inferential method to use. The second step with statistical inference is an area that's referred to often as confirmatory data analysis. The first step is exploratory. The second step is confirmatory. And here's where the tools of statistical inference are used. Most of the time when we conduct a study to investigate a question of interest, we're not conducting it on an entire population. We wouldn't have the resources, time available to us to conduct a study with an entire population. So statistical inference and the tools of it allow us to collect data on just a subset or a sample and try to make conclusions or inferences about the entire population based on that sample. And it's this area of statistical inference that allows us then to assess whether one hypothesis appears to be valid as opposed to another. And it's this area that allows us to make comparisons between groups, assess the statistical significance of these comparisons, and also make future predictions. So these are the two areas that we'll be focusing on. The statistical inference is really what we see typically reported in a journal article. It's the inference that allows us to surmise or conjecture what's true or likely to be true. So let's think about that for a moment. We never really know the truth because we're collecting information that's carried out in a study on a sample of individuals, not in an entire population. So we can never be 100% certain about anything, The best that we can do is use the tools of statistics and the tools of probability in the methods that we use to try to conjecture what's likely to be true or based on our data or observations may be more likely to be true than other hypotheses. So that's where we're going with statistical inference, to try to use the tools to be able to be fairly confident in our conclusions, but we're never 100% certain. So this leads into a discussion about some of the key ideas in statistical reasoning. One is that natural laws don't perfectly predict phenomena. Now, what do I mean by that? It means that there's always an amount of uncertainty associated. We can never perfectly predict an outcome or a response with a therapy. We can never perfectly predict a measurement. There's always uncertainty associated with it, and there's always variability across individuals or observations. So in statistical reasoning, we use the rules and tools of probability and probability models, and I'll define probability in a little while, but probability really means what's the chance or the likelihood of something occurring. And we'll use probability to help us both quantify the amount of variability we have, as well as quantify the amount of uncertainty we might have in a set of observations. So variability is natural. We expect to see variation in observations. Unfortunately, though, variation leads to uncertainty, and although we have variability in data and uncertainty, it's the patterns that we're aiming to detect with statistical methods, and the patterns that allow us to then make a decision regarding one hypothesis or another. Although we won't be spending time on study design, I think it's important to realize that there are different sources of variability or variation in the data that we may be looking at. Think of the example of blood pressure. There's certainly natural variation. There's variation that's across individuals based on ethnicity, based on age, based on gender, based on disease status. So there's always natural variability that will be inherent in the data that we're looking at. There's another type of variation that's measurement variation or error. So depending on the type of instrument that's used to measure blood pressure or the methods that are used in using the instrument to measure blood pressure, there may be variability. What are two key definitions then that we should keep in mind? One is bias, and bias is just the difference between an average value of a measurement in a sample and the true value. So the bias is the difference between what we get as an average and what the truth is, whereas the variance is the variability that we actually see in observations about their average. So both are variability, but one is looking at the difference between what we observe and what is the truth. Variance is the variability that we see in a set of observations about the average. So two different sources of potential error, bias and variance. A study is usually conducted to try to decrease or minimize both of these, minimize the bias and minimize the variance. At the stage that we'll be talking about and using descriptive statistics and inferential methods, we'll be dealing with the natural variability, and we'll be aiming to have a data set that has little bias based on the fact that it was a carefully conducted and executed study. Okay, so how can we summarize what the points that I've been trying to get across? One way is to look at biostatistics as a paradigm. What is biostatistics really attempting to do? It's really attempting to look at simple explanations for natural phenomena, meaning how do we explain the associations or the relationships or interrelationships between different variables. So there's a couple of key words here that I'd like to emphasize. One is explanations. What's another word for explanations? Hypotheses about how something works. So we're looking for explanations. We're trying to assess the evidence for or against different hypotheses about how things work, how mechanisms of disease work, how treatments work in society. We're doing this on the basis of variables, data that we've collected that indicate different characteristics. So what's a variable? It's just a characteristic that takes on different values. Blood pressure is a variable, age is a variable, a response is a variable. And the explanations that we're aiming for are ones that we really are hoping to be simple. Now often there are very complicated statistical analyses and methodologies and models that can be created. Biostatistics, though, is really aiming for the simplest model that can accurately explain relationships between variables. And so you may sometimes hear of the principle of parsimony, or especially with multivariable models, the most parsimonious model is one that really is aiming to get at the simplest way of explaining how relationships or mechanisms work. And those interrelationships can be classified as associations between different variables and potentially causal connections. So does a treatment result in a better response? Does treatment A result in better response than treatment B? Is there a relationship between an exposure variable and disease status? Now, I defined for you what a variable is, just a characteristic taking on different values. Some of the underpinnings of the methods that we'll be looking at are that we can think of when we do a study and collect data that we're really collecting data that reflect a random variable. And by that we mean a random variable is a variable that takes on values as a result of chance. some combination of chance characteristics. So in a population from which we take a sample, we know that some individuals may have different characteristics which then influence their responses, and the response then is variable because it might be influenced by the treatment, but the response is also influenced by other chance factors that are namely the demographics and other characteristics of the individuals. Now, I had mentioned before that not all variables are alike, and so in handling variables, we typically define some outcome measure that can be thought of as the response variable or the dependent variable. And the response variable is a variable that appears to be affected or possibly caused by other variables. Those other variables are what we refer to as the explanatory variables, the independent variables, or covariates. So these are all synonyms for the same thing. Response or dependent variable or outcome are all the outcome measures that we're interested in, whereas explanatory variables are the covariates or the independent variables which act upon the response variable of interest. And all of the variables are not alike because they can be measured on different measurement scales. So I've tried to set the stage a bit here for the theory that falls underneath statistical inference. Now we're getting more into the nitty-gritty. So the types of variables that we have can either be considered as a quantitative variable or a qualitative variable. So what's a quantitative variable? By definition, it has the attribute of amount or number. It's a numerical variable. And what are some examples we can think of? Well, there are types of quantitative variables, ones that are discrete, meaning there are gaps in the values that it can take. So a discrete random variable, for instance, is looking at numbers of deaths, numbers of births, whole numbers in which we can't possibly have 1.5 deaths or 1 3/4 deaths. So it's a discrete variable, it's a count. So counts can be considered quantitative variables, but they're discrete in nature. On the other hand, there are continuous variables that have no gaps in the values that they can take. What are some examples of those? Well, age is a continuous variable. Blood pressure is a continuous variable. Height, weight, others you can think of? Anybody? Any value that has no gaps in the possibilities of values it can take. So we can look at age measured in years, but we can look at it measured in months, in days, in minutes, if we chose. So it's a continuum. A discrete variable, on the other hand, still implies the concept of numeracy or count, but it has gaps in the values. On the other hand, there are qualitative variables which imply attributes or categories. And these can be measured on a nominal scale, in which we're looking at the names of variables, or on a ranked or ordinal scale. So on a nominal scale, examples that come to mind are ethnicity. So there's no implicit ranking or ordering. Ethnicity in terms of Caucasian, African American, Asian American. So these are all variables that imply a quality or an attribute, but have no ranking associated with them. On the other hand, there are variables that have an ordering, an implicit ranking or ordering. So what are some you can think of? Education is one, in which we might have less than grade school, high school, college. Others that you are bombarded with all the time, not necessarily even in the workplace, are Likert scales. On a scale from 1 to 5, do you strongly disagree, agree, up to strongly agree? So Likert scales. So these are different types of variables which are handled analytically in different ways. And we'll be coming back and looking at examples of these as we go on. So what is one simple example that might allow us to incorporate some of the information that I've covered already? I'm going to give you the example of a very large randomized community trial that was carried out in the northern part of Indonesia, in Aceh, Indonesia. It was a trial that was looking at vitamin A supplementation. And actually, villages were randomized for children under the age of 5 to receive a 3-cent capsule of vitamin A or a placebo that did not include vitamin A. It was a very large trial, 26,000 children. The recommended international units of vitamin A were given at 1 to 3 months, and then again after 6 to 8 months. And at 12 months, there were still 23,000 of the 25,000 children who were then followed at 12 months for vital status. And so leading up to this large community randomized trial were scientific investigations which seemed to indicate that vitamin A may reduce both nutritional blindness as well as mortality. And so the hypothesis was whether or not there was a difference in mortality between children who were treated by vitamin A versus those treated by placebo. So what we have here are a number of variables. We have, well, let's see if we can name some of the variables. We have the treatment, which was vitamin A versus placebo. So this is a qualitative variable of vitamin A versus placebo. We have an outcome, which at 12 months was looking at vital status, which again is qualitative, dead versus alive. But in terms of the counts of children who were still alive at 12 months, we have a quantitative variable. It's a discrete variable because it has gaps. It's only in whole numbers. And how might we look at this information in a table? So here's just a cross-classification table of, on the row tab, we see here vitamin A, no or yes, so placebo versus vitamin A. And then on the columns, we see alive at 12 months versus not alive. And so the total of 23,682 children can be cross-classified by vitamin A status versus vital status. And the question of interest here is, does vitamin A reduce mortality? So in order for us to answer that, we have to summarize the information in this table in some way. And one way of doing that is to look then at the mortality rates. So how would we calculate the mortality rates? We could flip back and look at the previous slide. You have that in your notes. But we can look at the group that has not received vitamin A. The number of deaths by 12 months was 74, divided by the number of children who had been randomized and received placebo, 11,588. So if we go through the math, and there's really minimal math in this class, but if we went through the math, we would see that this is 6.4 deaths per 1,000 children. And this was all at 1 year status, so we could call this 1,000 child years. And if we look at vitamin A group, the vitamin A group had 46 deaths divided by 12,094 children, 3.8 deaths per 1,000 child years. So on the surface, what would you say? Does vitamin A appear to reduce mortality? It appears to. How could we, though, better summarize this information? We could calculate a risk ratio or a relative risk. We could look at the rate in the group with vitamin A divided by the rate in the group without vitamin A. And we see we get a ratio here of 0.59. So this ratio of 0.59 we could compare to a ratio of 1. If there was no difference in the mortality rates between the two groups, wouldn't we expect the ratio to equal 1? So based on this, a ratio of 0.59 is 0.41 below 1. So we can think of taking 1 and subtracting 0.59 to get a value of 0.41, which would indicate approximately a 40% reduction in mortality. So a study was carried out in order to try to provide evidence for or against a hypothesis. We have a summary measure here. What we don't know yet is how can we make a statement regarding a 40% reduction in mortality and make a conclusion about whether or not this is something that we would have observed just by chance alone, even if there was no difference between the two groups. So over the next few days, we'll be trying to set up methodology for assessing that. But our question here is, does vitamin A cause this reduction? We don't know. We're aiming to look at whether there's an association between reduced mortality and vitamin A supplementation. We don't know if it causes it. this was a study design that used randomization. So the fact that we had randomization, the two groups, those who were treated by vitamin A versus those who were not, were as alike as possible for all characteristics except for the treatment. So the causal relationship is one that we may be able to glean based on the role of randomization. But there are a number of other issues. We know that the study was carried out in just one small part of Indonesia. Would we really get the same results if this study was performed again in the same area? Would we obtain the same results if the study was performed again in a different area? Those are questions we can't answer with statistical methods. What we can answer is how strong is this evidence that vitamin A works. So again, we'll be setting up the framework for trying to address that question. So in the next 25 minutes, I'd like to introduce to you some exploratory data analysis techniques. And I can't overemphasize the importance of looking at your data. There's often this temptation to move ahead and perform a t-test or an analysis of variance or a multivariate model without first looking at the data. And it's important to look at the data. It's important to check the distribution of the data to see if there may be mistakes or outliers in data collection or entry. It's important to look at the distribution and gain some insight into the distribution of the data. And as I said, check for any errors or mistakes. Many of you are already familiar with methods for looking at data and have seen data presented in some different ways. I'd like to take us through a number of methods that range from ordering the data to grouping the data to summarizing the data and then displaying it in tables and graphs. So the first aspect is to first look at how we could look at ordering the data. All of you are familiar with tallies. There's a specific technique called a stem and leaf display that was initiated by Dr. John Tukey that is a very helpful tool. And although we'll be going through this looking at performing a stem and leaf display by hand, there may be opportunities for you in the future to use a statistical analysis package or to interpret data that are in stem and leaf displays from colleagues or working in research teams. So let me take you through a very simple example. Suppose that I had taken the ages of the first 10 students who had walked through the doorway today. And in fact, what we saw that the first student was 35, and the next one was 40, and then the last of those first 10 students was 35 years of age. So we know that we could sort of tediously calculate the tally by just ordering these all by hand, finding that the first one was 27, the second one was 28, the third one was 31. And if we put a tally here, we would see that there are 2 in the lowest and in the highest groups. There are 3 in the middle groups. But what we've done is by tallying it in this way, it was tedious, but we've also lost some information. What kind of information do we lose? We lost the order they came in, but we also lost the second digit of the age. So we knew there were 2 in the 20 to 29 age group, but we don't know if they're both in the low 20s or in the high 20s. So there's a technique that you can do by hand or a computer can do called a stem and leaf display, in which we set up the stems of the distribution to represent each of these 10-year age groups. So the value 2 here represents the age group 20 to 29. The value 3 represents the age group 30 to 39. 4 represents 40 to 49, and 5 represents 50 to 59. And then if we've set up the stem of the display, we can put the leaves on the stem and leaf display, and the leaf for each age is just the second digit. So I could take age 35 and place the 5 down here in the age group that it begins with. I'd go to 40, place the 0 in the next bin. 52, place the 2 in the age interval 50 to 59. 31, place the 1 in this interval. Do you see what I'm doing? So all that I'm doing is I'm not ordering the observations to begin with. I'm just going in the order in which they came in and placing the age, the second digit of age, in the appropriate age group. So now I can easily go to the next step, which says, are these ages ordered within each 10-year age interval? The first one is, what about the second? It's not ordered, but I can easily order it so that 31 goes before 35. And the next one is ordered already. The last group, I would reshuffle this so that I would follow 50 by 52. And in a flash, I can see some information about this distribution. Well, what can I see? I can see a couple of things. If I could turn the computer on its side, so if you turn your heads to the side, you would see that actually what you have is a histogram. So this is just a histogram on the side in which we see a rather symmetric distribution, rather symmetric. Most of the observations are actually in the middle age groups, but there's an equal number in the lower and in the upper. And at a glance, I can see that the lowest age was 27 and the highest age was 52. So this is a very useful technique for just looking at the data. I see that there aren't many gaps in the values that these ages can take. I don't see any ages that are 9. I don't see any ages that are 92. So I can easily look at this. What you may have seen more frequently, rather than a stem and leaf display, is a frequency distribution. So a frequency distribution just takes the actual frequencies or counts in each age group. So we see out of these 10 students, 2 are in the first group, 3 in each of the middle age groups, and 2 in the last age group. And so a frequency distribution is nothing more than just a distribution of the counts in each age group. A frequency distribution, though, isn't very helpful if we wanted to compare, say, males to females. Especially if we had 10 females and 25 males. So another way of grouping data is to look at a relative frequency distribution. A relative frequency distribution just looks at the count relative to the total. So a relative frequency distribution shows us the percentage distribution or the proportions or fractions of the fraction of individuals in each age group. So what we would see here is that 20% of the total are respectively in the youngest group and in the oldest group, and 30% are in the 30 to 39, 30% are in the 40 to 49. So if we actually had two samples that we were interested in comparing, we would compare these relative frequencies that are already adjusting for the total number in each group, as opposed to comparing the frequencies or the counts themselves. Another way then of looking at that same information is by looking at a histogram that we see here, just another way, a graphical way of seeing that 20% fall in the lowest and the highest age groups, 30% fall in the middle groups. And if we added all of those fractions together, they'd sum to 1. They'd sum to 1. So a relative frequency distribution always will sum to 1. There are a couple of other ways of looking at frequency distributions. We could look at a cumulative frequency distribution, which simply gives us, if we look at the column I'm pointing at right now, which are the counts in each age group, the next column gives us the cumulative counts, or the cumulative frequency, that we would take by just summing the counts in each group or any lower group. So if we sum 2 plus 3, we would see that there are 5 individuals that are in the 30 to 39 group or something lower, 8 that are in 40 to 49 or something lower, and all 10 of them can be considered to be in the 50 to 59 age group or something lower. So the cumulative frequency is just summing up or counting the actual frequencies. And just as we saw we could calculate a relative frequency distribution, we can do the same with a cumulative relative frequency distribution. It's just that once we have the cumulative counts, if we divide it by the total, we would see that 20% fall in age group 20 to 29, 50% fall below age 40, 80% fall below age 50, and 100%, or a fraction of 1, fall below age 60. So just some simple ways of being able to group data, present it in ways that one can make comparisons. Now, all of you as well are familiar with percentiles. Maybe don't deal with them on a daily basis, but we could define a percentile as the value that's greater than or equal to R% of a sample of n observations. So the 90th percentile is the value at which 90% are less than that quantity, 10% are higher. And there are some specific percentiles that come in very handy in describing data. The three that are listed here are the 50th percentile, which also is known as the second quartile. That's just the median. So the 50th percentile says 50% of the observations are below this point, 50% are above. And if we think of the median, it's the middle value. Sometimes it's the average of the middle two if it's an even number. But think of it as just the middle value in a distribution of data. How can we think of the 25th percentile and the 75th percentile? I think the easiest way to think of the 25th percentile is that if you just limit yourself to the lower 50%, the lower half, then the 25th percentile is the median of that lower half. Does that make sense? And again, the 75th percentile can be thought of as the median of the upper half, the median of the upper 50%. So these percentiles of 25th, 50th, and 75th also go by the names of the first, second, and third quartile. So let's go back to this example with the student ages. We had, remember, 10 student ages. Here they are ordered so that we can look at these and figure out what the corresponding values for the second quartile, the first, and the third. Now, what's the median here? There were 10 observations. So since it's an even number of observations, it's actually the average of the fourth and, well, let me ask you, what are the middle two observations out of a number of 10? The fifth and the sixth. So we would count over to the fifth observation, which is 35 years, and the sixth observation, which is 40. And the median then is just the average of those two ages, which would be 37.5 years. So think of an imaginary line here, 37.5, that says 50% of the student ages are below that, and 50% of the student ages are above it. Now, what about the lower quartile, which we said was the 25th percentile? Think of the lower half. The lower half are these first 5 observations. What's the middle of those first 5 observations? 31. So the 25th percentile, or the first quartile, is the value of 31 years. And we can do the same for the upper 5, or the upper 50%. The middle value is 43. So the 75th percentile, or this upper quartile, is the value of 43 years. So those are some descriptions. Let's just go back to that for a second, because this says that the median age is 37.5, the 25th percentile is 31, the 75th is 43. So that means that the middle 50% between the 25th and 75th percentiles ranges between 31 to 43 years of age. So we've just talked about one measure of what's referred to as central tendency, and that's the median. So the median, as a single summary measure, tells us about the middle observation. The other measures of central tendency are the mean, or the average, the simple average. And a third common measure is the mode, or the most frequent observation. If we go back and looked at our student ages, do we have a mode in this distribution? We do, because we have 2 observations with 35. So we have a mode, we have a single mode. We may have a different data set that has 1, 2, or 3 modes. This one we just have 1. But as well as what's the central tendency, or the inclination of observations towards the middle, we can look at measures of variability, or spread, or dispersion in a data set. And we already have looked at the difference, the largest value and the smallest value in our data set. The range is defined as the difference between the largest and the smallest value. That's one measure of how variable or dispersed the data are. Other common measures are the variance and the standard deviation. So here I'll just give you the definition. The variance you can think of as a type of average of the squared variability of each observation from its mean, And the standard deviation is the square root of that. Let's make some sense by taking this back to the example. So here's that example again. We calculated the median already of 37.5 years. We could, if we summed all of these ages and divided by 10, we'd calculate the mean, and the mean here is 38.3 years. So the mean is a little bit higher than the median. The mode, though, we already said was 35 years. What about these measures of dispersion or variability? The range, we said, was the difference between the largest and smallest values. So 52 is the largest, 27 is the smallest. We have here a range of 25 years, 25 years. How would we calculate the variance? If we thought of taking each of these ages, subtracting the mean, which we calculated as 38.3, squared that difference, and divided by the total number of 10, but subtract 1 first and divide by 9, we would get the variance, which is in squared units, this is in years squared, of 74.7 years squared. And with your homework, you can get some practice in making this calculation. Most of the time, you'll just have to interpret it. And most of the time, what's really used, rather than the variance itself, is the standard deviation. So the symbol that's used for the sample standard deviation is S, and it's just the square root of 74.7 years squared, which would give us 8.6 years. So this is a measure of variability in this data set of ages that we'll be using as we go along in the course. Now, there are a couple of other definitions that are often used in summarizing data, and I'd like to make sure that we have these all defined before we go on. A ratio is just one number divided by another. So we could have A divided by B is a ratio of two quantities. A proportion, though, is a special type of ratio, and one that we'll be using more in this course. A proportion is a ratio in which the numerator is explicitly a part of the denominator. In other words, the numerator is a subset of the denominator. Whereas a rate is also a ratio, the only difference is that calendar time is used in the same way in the numerator and the denominator. Those are the definitions. How can we make some sense of these by looking at examples? So what would it be an example of a ratio in this simple data set? Suppose I wanted to look at the ratio of the number of students over the age of 40 to the number of students under the age of 30. So over the age of 40, we have 4 students. That's the numerator. Under the age of 30, we have 2 students. So the ratio of 4 divided by 2, or 2, is what we would say is the ratio of the number of older aged students compared to younger age students. We could define specifically a proportion, though, as looking at the number of students that are over age 40 out of the total. So it's still a ratio because we have a numerator divided by a denominator, but the numerator, which is 4 students over the age of 40, is a part of that overall total of 10 students. So a proportion takes a numerator and divides by a denominator, but the numerator is a subset of that denominator. So we could say, what's the proportion of students over age 40? It's 4 divided by 10, which is 0.4, or 40%. A rate, we said, is still a ratio, but it needs to bring in calendar time. So we may look at, as of July 1st, the number of, say, new students divided by the number of students who are enrolled in a course or a program as of July 1st. So This is a particular type of ratio. It's special because it brings calendar time and uses the calendar time in the same way in defining the numerator and the denominator. Okay, well, I cannot introduce exploratory data analysis without telling you both about the stem and leaf display as well as the box and whiskers plot. So if you hadn't guessed by now, the same person who's responsible for the stem and leaf display also coined the term for the box and whiskers plot. So let's talk about what a box and whiskers plot is with this little data set. And these are actually plots that you will be seeing and have been seeing more frequently in the published literature. They used to be plots that were simply reserved for looking at the data before it may go into a journal article. But you may see that you'll actually see a box and whiskers plot in a journal article now. So how did Dr. Tukey define a box and whiskers plot? Well, first he said, let's talk about a box that shows the middle 50% of the data. So if you think of the upper hinge of the box and the lower hinge of the box, the upper part of the box is the third quartile, or the 75th percentile. And the lower hinge, or portion of the box, is the first quartile, or the 25th percentile. That forms the box, and then a line can be drawn in the box which shows the median. That means that then we're able to display what's referred to as the interquartile range, the middle 50% in the box, and draw whiskers from the box that show the extent of the data. And there's also a definition for identifying values that don't appear to be consistent with the majority of the observations, and those are what are known as outliers. So there are some guidelines that are set in this terminology called fences, in which think of if you have the middle 50% of observations, the interquartile range, and if values are actually 1.5 times that range above the upper quartile, or if they're 1.5 times that range below the lower quartile, there might be something wrong with them. So let's look at an example to make sense of this. Here's our student data, our 10 students, just shown in a box and whiskers plot. So if you will recall, what was the median value? The median value, or the middle quartile? 37.5 years, 37.5. That's the line that's drawn in the middle of this box. The box itself is showing the middle 50%. So if you refer back, the lower quartile was 31, and the higher quartile was 43. So this range that goes from 31 to 43 shows the range of ages for the middle 50%. The middle 50%. These are the whiskers. These are whiskers drawn up to the highest observation in the data set, which was 52. And then a whisker that's drawn down to the lowest observation. Do you remember that age? Which was 27. So as opposed to just talking about a single summary measure of a mean or a median or a mode, we can see in this display all the data from the maximum value to the minimum value. We can see the middle 50%. We can see the median, all in one graphical display. Now, this happens to be a data set that doesn't have outliers. But what if we were trying to determine whether there were outliers? If I take you to the interquartile range and look at this distance, remember that was from 31 to 43, so that's about 12 units in age, 12 years. Think of multiplying 1.5 times 12. What do you get? 18. So if there are values in the data set that are more than 18 years above the upper quartile, that would have been 43 plus 18, which is 61. Our highest age was 52, so there were no outliers, no values that were above that fence. Does everybody see what I did there? Let's do it with the lower fence. This value, again, the interquartile range we said was 12. So 1.5 times 12 we said was 18. If we looked at 18 years below the lower quartile of 31, 31 minus 18 is 15. So any ages below the age of 15 would be considered low outliers, low outliers. So in this particular data set, we had no outliers. If we had a 12-year-old student or a 10-year-old student, we would have indicated them by dots below the whiskers, or if we had had a 92-year-old student, we would have indicated that student with a dot above those whiskers. But the point of the whiskers is that they go to the data, the observed data, that are within the data set, that are within the fences. Otherwise, any other observations are indicated by dots. Okay, well, what might these also be useful for? They allow us to look at a description of two groups. Suppose I had males and females, and that indeed I can see very different patterns in these boxes. One is shifted up. The females tend to be older than the males. In fact, if we look at the median that's shown here in this box, this says that 50% are above the age of about 42 for females, whereas about 50% are above the age of 35 for males. We can see the ranges are fairly similar, but the distributions in the middle 50% are very different for these two groups. So we're able to display the data in this way. So I hoped to give you just a flavor of ways of looking at the data by looking at a distribution with a stem and leaf display, by looking at a box and whiskers plot, to give you, to remind you about common summary measures that are used for central tendency and that are used for variability. I had aimed in this first period to look at defining biostatistics in the context of exploring hypotheses and to recognize the fact that we're going to be dealing with uncertainty and variability all along the way, that the variables that we collect are often different, but that our very first step before proceeding to the level of inferential statistics is to look at the data, use some of the descriptive statistics and exploratory data analysis tools in order to identify patterns, become familiar with the data, and then proceed from there. So this is where we will end